today, it's like a great pleasure to introduce today's speaker, Professor Zach Ulissi. Professor Zach is basically like a senior, he's a senior research scientist manager at Meta Fundamental AI. And since 2024, he's also an adjunct professor in the chemical engineering department at KMU. And before joining Meta, he was also an associate professor at KMU. And Professor Zach obtained his PhD from MIT and his postdoc from Stanford, where he worked with Professor Norskov to simplify complex catalyst reaction networks using machine learning techniques. And without any further delays, I will leave the floor to Professor Zach. So,
for the intro, and thanks for the invitation. It's fun to be here. I would say Berkeley is a hard place to give a computational materials talk because there's so many people in this space that it's really hard to even know what is sort of the baseline knowledge. So just for my own benefit, how many of you would say that you're in computational materials? Okay, so how many of you know what inorganic formation energy is? Okay, good, excellent. How many of you know what a graph network or machine learning potential or message passing? Okay, the number's going down a little bit. To be honest, like not so far from what I expected. Again, you guys are right there with the state of the art and doing all this fun stuff. So I'm going to try and be a little bit light on the details. But if there's anything that's not obvious, please feel free to stop and ask questions. And if you think there's anything you want me to dig into or other stuff, feel free to just tell me. Also, if you think I'm covering something that's like way too obvious or basic, also feel free to like raise your hand and say, Zach, this is ridiculous. We know what you're talking about, okay? Okay. But so the first thing I wanted to say is this is the view from our office. If you look out across the bay, we can see you all from the top floor of our building. So my point is just that we are all very close. We are super lucky to be part of this like Bay Area material science AI chemistry community. It is literally like get on the BART and then take it a few stops and then you end up right next to our building. If you ever want to come and say hello or have lunch, feel free to just send me an email or a message on Slack or however you can find me. We can host up to 20 social visitors a year. I've never gotten close to that limit, so it's not hard. The entire chemistry team sits in this building. So also most of the people who are most relevant to the stuff that you're working on, again, they're literally like right across the water. The second thing I wanted to say is when I was coming here, I was starting to think about who else did things at Berkeley. And so we don't have a big team. We have like, I don't know, 12 to 15, depending on how you count full times in program managers and other stuff. But roughly half of the chemistry team right now did either undergrad or PhD at UC Berkeley. So just if you're looking for other people to chat with or career paths or just want to make connections or whatever, there's a ton of people, a lot were at Berkeley or came through here. That is both people that you could chat with if you ever want to reach out. And also thank you to the Berkeley community for having such awesome educational opportunities and training people like you. Like we all benefit. So to give a little bit of background on the chemistry team, most of what FAIR, which is fundamental AI research, is known for is things like the original Llama. Llama models are actually a different organization within Meta now. So that sort of graduated to be more production. But large language models is a lot of the work. Vision models, how many of you have heard of segment anything? A few. If you have any friends doing microscopy and manual segmentation or like trying to count leaves on a plant, tell them to like stop and start using things like segment anything. There's a bunch of cool tools that have been developed there. There's a group doing embodied AI, which means like robots with goals and actions and things. That's, I would say, gotten extremely popular in the last year or two. And then speech, so things like language translation, probably the most well-known has been this effort called No Language Left Behind, which is basically trying to move translation from just the most common 5 languages to basically being able to go in between any 2 languages that's spoken anywhere on Earth. So that's most of what FAIR is associated with. One of the reasons why I really enjoy being at FAIR is of the industrial AI labs, FAIR is one of the most committed to open and reproducible research. So that means that all the stuff I'm going to talk about today, it's already published. Most of the data sets and models are available. You can do whatever you want. Makes it really fun to go around and give talks and collaborate. We have a FAIR Bear intern working with us in the day-to-day. And so it means that we can sort of have a different operating mode than some of the other labs. We have a lot of compute. When people think about the industrial AI labs, normally what they think of is like a lot of GPUs in one place. And people have been like really aggressive at building these huge GPU clusters for training models. That's sort of what I associated. What I didn't quite understand was also how much compute there was at a place like Meta for just general data centers. And those data centers are not quite the same as you would find in an HPC system, like sitting up at LBL. They're not always like the fastest interconnects. But if you have a whole bunch of quantum chemistry calculations that you think are important and you want done, then we can leverage those resources. So when you're not talking with your phone to Instagram or WhatsApp or Facebook or whatever, at this idle time, basically they're running our simulations in the background. And that's a super cool resource because often it's the data that's missing. It's not just the models. We also need the corresponding data sets. And again, this wasn't like so obvious to me when I started working with them that there was this cool resource available. So the chemistry team has historically focused on things like catalysis and direct air capture, but I would say the entire field of computational chemistry and materials is getting more and more generalizable. So I'll talk a little bit about that. We've been working with material science. We've also been working some on display materials for AR, VR. So if you go and you look for job positions at Meta and you type in material scientists or whatever, sometimes you see our team. If you look for positions, there's also a big group of card-carrying material scientists. A lot of them either in the Bay Area or up in the Washington area that do materials for like headsets and AR, VR. Basically everything about those are interesting challenges. Okay. I thought I would start with an example that is actually relevant. So people, even after I give a slide like this, they still ask me like, why is Meta interested in material science or chemistry or whatever? So I feel like I just have to keep on saying the same thing over and over. But this is one example that I think is sort of a cool one. How many of you have heard of moissanite for carborundum? How many of you are actually material science? Okay. You look very bored. It seems like you really know carborundum. Okay, so tell me a little bit about it.
Yeah.
Excellent. Okay. So it's called moissanite because it was discovered in by Henry Moissan. It was basically part of a meteorite that they found. It comes up a lot in the earth sciences community because when you find these meteorites and everything is burned off or decayed or scraped away, often the thing that's left is this mineral, and it is super, super, super hard. So it's usually one of the things that remains that you can do an analysis of. And this is additionally even more interesting. I gave a seminar at the University of Chicago a couple of months ago. They let me know that the oldest material on Earth that you can point to and say what is the age of is a piece of moissanite that came from a meteor. Basically, it was floating around basically since the beginning of the universe out in space for billions of years. And it got unlucky, it hit the Earth and it settled down, and then someone picked it up and did a special dating technique. And that is the oldest thing that you can point to and say, I know the age and it's billions of years old. It's also super cool. Unlike most dating techniques where you look at like radioisotope decay, probably a lot of you have heard of that, they actually look at radioisotope increase. You basically measure how long it's been floating around by how many gamma rays have hit it. And so the more defects you have, the longer it's been sitting in space getting hit by this stuff. It's a super, super interesting thing. It's also very pretty. I like these little pictures of little colors, and it has these really nice, interesting grain boundaries. Anyone know why this is interesting to Meta? What's the connection here? Any guesses? Zero. Something to, okay, fair enough. I told you that was it. You were listening. Congratulations. If any of you saw the announcement for this Orion headset, this was announced at Microsoft or at Meta Connect in the fall. This is a silicon carbide waveguide. Basically, the thing that bounces light from the edge of the display to the center and then into your eye. That's what basically allows you to have an augmented reality display. That's a silicon carbide waveguide. It is a super high refractive index material, one of the highest we know. It's very stable. Unfortunately, it's also very hard to manufacture. The same thing that makes it so hard and lasts so long also means that it's really hard to cut and polish and process. So we can make displays like that, but I would say they're not like super cheap right now. But nonetheless, it was fun to see people like Mark Zuckerberg go up on stage and talk about why material science is so important. As a material scientist at Meta, that was like very fun to see. People really do care about these things when the opportunities don't exist. Okay, so just to make this concrete, you all said you know what formation energies are, so I'm not going to go into a ton of detail. Basically, We have different compositions. Silicon carbide sits in the middle. Usually the way that we look at this stuff is we say, there's a bunch of carbon polymorphs, so graphite and graphene and a bunch of things. There's a bunch of silicon ones. There's very few materials that are known to be stable at roughly 50-50 or any composition silicon carbide. This is all coming from the materials project. So I thank you to that community for having these resources available. Super, super, super fun to see. There's a bunch of things here that someone in the materials project hypothesized and are completely ridiculous. Like, there's no way that those things are going to be synthesizable. They are way too far above the hull. There's just no way that's going to happen. There's a few things here that look like they're sort of close. It's really hard to say, will it show up in real life? But those are the ones that, if you had to point to something, they might be interesting. And this is super important for something like silicon carbide because there's actually a few different polymorphs here that are basically all very, very, very close to zero energy above hull. And some of these polymorphs are absorbing. So actually the picture I showed you of this material, you can't look through that material, right? That looks black. If you make a display out of that, you're not actually going to be able to see through. That's not what you want. But one of these polymorphs actually is high index and transparent. So I'm just basically trying to remind everyone that the ability of computational chemistry and material science to predict things that are relevant to industrial devices is very high right now. There's a ton of work that's been done in that community to make that possible. It's super cool to be able to take those things and then apply them to these real use cases. Okay, so that's about silicon carbide. That's basically just motivation for why Meta might be interested in some of these things and why we might want to build models to predict formation energies. But again, you all know this. Computational chemistry has come a long ways. I'm not going to go into the details, but I think it's worth, whenever we have one of these talks, just remembering how much work was done to get to this point. It didn't just happen overnight. There was like 30 years of people hammering away on computational techniques, deciding what are the right pseudopotentials, what are the right approximations, making these things. Like, we shouldn't take all of the amazing work that the physicists did to get it to this point. And we happen to be sitting at a special point in time where the methods started to get more transferable and also compute started to get more cheap. And so the ability to even run these ab-initio simulations and get something that correlates with experiments, we are, again, very, very lucky to be doing this sort of work at this time right now. It's a super cool opportunity. Most of the models I'm going to show you, normal DFT codes, often hundreds of thousands of seconds. Most of the models that we try and do are normally on the order of 1/10 of a second. So roughly, we're about 1 million times faster. 1 million times faster is not infinitely fast. If you talk to people doing classical potentials or biology or whatever, they'll still tell you that your models are slow. That's okay. But 1 million is still pretty darn good. And so that's most of what I'm going to be talking about. And of course, this is Berkeley. If you look at like one of the machines, like I think this was NERSC 10, which was Perlmutter, roughly 1/3 of all the compute in something like Perlmutter goes towards running these DFT codes. So also just so that as a community, we should be thinking about just how much of all the processing power is doing this and how often do we actually run a calculation where we're actually getting something new. And I think in many cases, we could have predicted what was going to happen. And the way that we can predict what's going to happen is through these machine learning models. Okay. So let's talk a little bit about some of these models and all the progress. How many of you have seen the MathBench Discovery Leaderboard? Let's see, about half. That is work that was started at LBL by Christine Person and Anubhav Jain and others, and a very talented visiting researcher, Janosch Ribasol. It's a public leaderboard, one of many in the material science and chemistry space. Has gotten a lot of activity in terms of different people submitting models, which has been really fun. There's a couple of things to look at on this. So I took the snapshot last night. I had to do it last night because people keep on submitting stuff constantly. I was looking at the slides and they were already out of date, and I gave them like last month. So this is like the mean absolute energy for predicting a formation energy for something that looks not too far from what you might see in the materials project. It's not like a wildly creative outer domain generalization case, but nonetheless, it sort of measures, if I wanted to put something into the materials project, how good could I predict that formation energy ahead of time? Not perfectly, but that's the way to look at that. There's a couple of others here. These are basically like, if you were using that to screen, is the material stable or not? How successful would you be? This one is a newer one that they added. I'll talk a little bit about that in the end. That's like phonon spectra, second derivatives, vibrational modes, also something that we want these models to be able to do well at. If you click the compliant one, you can do a little sort here, and you can sort on MAE or phonons or whatever. All of these compliant models were trained on the same data set, which is sort of nice because it's at least sort of apples to apples. Again, kudos to the materials project for standardizing things and getting the community to this point. Like, cannot overstate enough how important that was to making things like this possible. So thank you. When you look at this data set, this leaderboard, there's two little meta symbols right now. So the one at the top is eSEN, which we released in March. The paper was online before that, but we finally got the checkpoints public then. And the second one is this Equiformer V2 dense denoising strategy. I'll talk a little bit about what these are. But I'm going to tell you just a little bit about some of the choices that were made for those. If you're interested, feel free to stop me and we can talk more about trade-offs or what we're doing in that space. But it's super fun to see how quickly the progress has also been done. Also, just when you look at this, like all of these are just in the last year or two, right? It's unbelievable how fast this community is moving right now. Any questions on this? Any questions so far? Any questions on the metric? Awesome. Okay. How many of you already know what eSEN is? Okay, this is good. I'm getting to a smaller and smaller number of people who know exactly what I'm talking about. That's I think that's the goal. So I wanted to highlight eSEN because this is an example. It's not like we said that there was this leaderboard and we're going to come up with a completely new machine learning potential. Like, that's not the way that we developed eSEN. eSEN is basically a model that we developed in the catalysis space called eSEN. And eSEN was actually a derivative of an earlier model called SCN, which was a derivative of an even earlier model, originally GemNet. We've sort of been forking these things as we go along. My point here is basically these models have been developed for many different purposes. Things that are good for one data set or one leaderboard also tend to be good for others. This eSEN model, if you had to point to like one thing that's quite cool, it's basically the special convolution that was developed. There's basically a particularly gnarly convolution that scales really poorly with the degree of the spherical harmonics you want in the representation. And because of the way that we were training models, and specifically we wanted our models to predict things like the energy, and we also wanted our models to predict things like the force directly. The force is a vector, and it requires a high degree of angular resolution to do that, because this thing can be anywhere. If you want to say it's in this direction, you have to be very precise. That was an incentive for us to find methods that were scalable with the degree of the spherical harmonics, so we could get really high harmonic representations. And so this was a trick that was developed by Larry Zitnek on our team. Originally, this was in NeurIPS. Basically, he found a way to reduce that. Larry comes from a computer vision background, so he thinks of everything in terms of 2D convolutions. Basically, he said, why don't we just treat this as message passing on a 2D grid? We'll do little convolutions there, and as long as we're careful about how we do the convolutions, we can come up with a method that's more scalable. So that's a long-winded way of saying that people have been making methodological advances in this machine learning space. Some of these end up being very useful down the road. And some of these models, even though they're new on the leaderboard, we're basically building on different bits and pieces. Again, it's not like one person walks into a room, sits down and comes up with a completely new architecture. Like, this field is moving so fast, everyone is playing different games and trying different things. So this eSEN model was quite good. But one thing that we did was in eSEN, we were trying to predict relaxations of small molecules on a catalyst surface. No problem. If you're doing a local optimization and you're just trying to find a local minima, it's not so bad if you just follow the gradient downhill. And that's not a bad way of doing an optimization. But sometimes you actually want to run a dynamic simulation and the energy is fluctuating and things are bouncing around. And in many of those simulations, you want things to be more energy conserving. And that's something that if you talk to a computational materials person, not 100% of the community thinks that that is like the most important thing, but it's something that a lot of the community was trained to do. If you take a computational physics course, usually the first thing they make you do is you write a molecular dynamics code from scratch. And usually the way that you debug it, because like you're going to get the integrator wrong, is you check, does it conserve energy or not? And if it doesn't, you have a problem. So I understand where the community is coming from. So the eSEN model worked really well, but we made some choices that meant that it didn't quite get the energy conservation right. And also there were some other choices, like there was an assumption that whenever it came time in a message passing network to collect messages, you just talk to the 20 closest people. And 20 is a pretty reasonable number. Like 20 is like usually the first coordination shell and part of the second. If it's amorphous and things are bouncing around, like it might even be a little bit more than that. But if you choose the first 20, you have a little bit of a problem. Sometimes you have 32 degenerate neighbors. And then it's a little bit arbitrary which 20 you pick. So that's a little bit annoying sometimes. And you have another problem where if I pick the 20 closest people in the room, and then one of those people moves a little bit, sometimes they go outside of the radius and another one comes in. And so you can also have little discontinuities as people flip across the screen, across this little boundary. So that's another one where like numerically, it's not a huge deal. The models still work well, they scale. There's a lot of nice properties of those models. But if you want it to be super, super smooth and conserve energy, you need to walk back some of those changes. So eSEN, this model that I'm talking about, is basically eSEN, where a talented researcher on our team, Shang, basically went through and evaluated what is the effect of every one of these different choices of, do I choose a cutoff or do I choose how many things? Do I make it smooth or not? What's the resolution as I do this convolution operation? How do I basically smooth out some of these effects in a way that sort of guarantees that you can't have a sharp discontinuity? None of these were magical on their own, but on the whole, it makes the model easier to use for some of these tasks. And that's what led to that model being the top on the leaderboard. So when you look at eSEN, it's really eSEN, just with a bunch of different choices along the way for exactly how we constructed that network. If you look at these plots, basically what it's saying is, these are energy MAE metrics. So this is basically how well does your model do at predicting the energy of a new configuration. These are phonon metrics. Basically, how well does your model do at predicting the second derivative, the local curvature? And if you look at some of these older models like Equiformer V2, that's actually a really nice model for predicting the energy. Actually, the eSEN models are not really any better than the old ones. Like if you just have a new hypothetical material and you say, what is the energy or what is the stability? It's not actually any better for that. The models were doing really, really good at that task. But if you want the local curvature and you want to do a finite difference in a second derivative, then this matters a little bit more. And so the smoothness becomes important for some of these other properties. Any questions on this? This sort of makes sense? Yeah.
So when people do stuff calculations in machine learning for high energy and things like that,
Yeah.
one of the things is always that they want their model to be differential, but it goes backward and forward.
Yeah.
Is that related to that?
Yeah, it's the same idea. So you have to be differentiable back to the parameters if you want to train the thing. That's obvious. If you want to be able to take a second derivative and calculate the local curvature, or you want to take the gradient of the energy, which is the force, and then include that in your loss function, now you need your model to both allow for the second derivative and also be numerically stable. Also in the machine learning community, people like to do things like chop precision as much as possible to make things fast. And if you do that really aggressively, like you would in a computer vision sense, even if your model supports second derivatives, it could just be you accumulate numerical noise and it doesn't work. And so these are different trade-offs you have. And it also manifests, it's a great question. It manifests also in this model is also slower than the original ones. And that if you want to predict the gradient, you now have to take a full pass to the model. This other model, Equiformer V2, has just one forward pass and it gives you the gradient and the energy both at the same time. So implicitly, you're taking a speed hit. You say it's better to be conserving, I guess, but the price you pay is it's about 10 times slower. And so you need to be comfortable with the fact that you're going to sample 10 times less and or you're going to get fewer independent configurations. But that's a choice that that you can make now. Yeah. Other questions? Yeah.
Maybe jumping ahead.
Yeah.
But I'm curious if you guys are working on any model distillation type efforts, because these potentials like Equiformer V2, those are expensive models. They have like the largest one is what, like 150 million parameters, something.
Yep.
You can't run that on your laptop. At least on my laptop.
Ask your advisor for a new laptop.
Are you planning any works for that? At least that you're able to talk about trying to work on?
Yeah, it's a great question. And it's sort of an obvious one. I mean, a lot of this stuff you can also just like look at what's happened in the language and vision space. And if it happened there, like the models got too big and then all of a sudden you needed them to be more usable, then maybe you fine tune or distill or find a more usable thing for the day to day. If I'm asking Meta AI for how I should feed my dog or how many cups of food I should give it. I probably don't need 500 million parameters. Like probably there's like something simpler inside of there. I don't need the fanciest model. And so there's going to be these trade-offs. At the same time though, like I was having this conversation actually with someone this morning who I met for breakfast before I came here. We're asking a lot of people to learn how to do these things. So you're a new PhD student, you come in, you say, I want to do materials discovery for, pick your favorite thing, direct air capture, whatever. Most people don't cover that in undergrad. Like you do your sort of basic intro engineering or physics courses, but you now need to tell them what is actually the interesting research class of materials? What are the problems that matter? How do you do experimental characterization? Because you need to read a paper, even if you're not doing the experiments, you need to understand what do they know or what do they don't know. None of those undergrads have ever done computational ab-initio calculations, or if they have, they sort of ran a toy Gaussian calculation. That's not real. So now you have to teach them ab initio and all the trade-offs and all the things that go into these. And these aren't easy, right? There's a whole bunch of settings there that you need to be careful about. You need to tell them how to be careful about the calculations and do the analysis and get things that are thermodynamically consistent. Now you need to tell them machine learning potentials, how to train these things or how to use them. Maybe there's a model distillation step there as well. And then you have to connect it all. I'm a little bit worried, like if we have too many things, that's just going to make it harder and harder. So just from like a simplicity point of view, I would like if there were models that just sort of off the shelf solve most of the problems most of the time. And if we get to that point where we agree that everything is working awesome, and then we have to distill some, and a really good user knows how to do that and does the right thing, that's great. But I'm not sure there's like actually that many people in the world who have like all of those different things and can distill it for exactly their task. And maybe that's short-sighted. Maybe someone will come up with a really nice package where you click a button and run a command and it generates for your data set and does exactly the right thing. That could also happen. But there's a lot of steps here. And like the complexity is awfully high. Yeah.
So I want to get more detail of the message pass. What kind of message will be passed? Is it equivariant messages and what's the body of?
So I'm happy to go into details afterwards. These are equivariant messages, higher order tensors that are going around. That's part of why these convolution operations get a little bit interesting. We've tried a lot of things in that space. I would say there isn't like one obvious thing that's worked. In some of the models, we have simpler things, and then we have more message passing steps. And some of the others, we have more complex representations early and then fewer message passing steps. It's also one of the fun things about the space is I haven't seen any single strategy win over a like 3 or 4 year horizon. Like every 3 months or every 6 months, someone comes up with a cool new model. That's like a feature, not a bug. Like, aren't we lucky to be working in a space where just every 6 months our models get better? And I've had a lot of trouble predicting exactly what's the one that's gonna win out. So I think what you're seeing is basically our group has tried like 10 or 15 different models since we've started about 4 or 5 years ago. It's sort of a different family or zoo of different possibilities. This eSEN is just one thing that works. But I'm happy to go into details afterwards. And again, Larry is really the person to talk with about cool new message passing steps. He loves to just chat with people about random things like that because that's like a very meaty, fun numerical problem. That's not like a super clear answer to your question, but it's a very deep question. So I don't want to spend too little time on it. We should talk about it afterwards. Yeah. Other questions?
Well,
okay.
Hey, Zach, one from the internet, if that's all right. So you mentioned briefly about trying to use different kind of numerical precision to try to speed up these models. And I know this, I think Allegro has tried this in the past, but I just want to kind of get a sense, like, do you know where, like what steps of the model have significantly large amounts of numerical error and which parts we can kind of get away maybe with lower precision?
So just to repeat back because it was a little bit late, I think the question you were asking was, in these models, there are different areas that require high precision and maybe some areas that require low precision. And so do we have any intuition as to which steps you have to be like full double precision, super precise, and in which areas you can be a little bit less? Is that the question?
Right.
Yeah. Some of these things, some of the ML some of the frameworks will do for you automatically. So like PyTorch, for example, has like this method called automatic mixed precision, which will go through and try and automatically determine which areas you could maybe get away with lower precision. I would say there's a lot of heuristics there. Ultimately, it comes down to just a bunch of experiments where you just try different things and then see which one works the best. Our experience with things like AMP is it works sometimes and it helps for training, but often it's a little bit hard to debug afterwards. So I think if you ask people on our team, they would say they don't have a great understanding of exactly what are the areas you can get by with the least. It's really an empirical science at the end of the day. And also these models are so complicated and the training strategies are also a little bit of an art at this point that I don't think there's like one right answer here. I think there's probably a lot of ways to get into the right approach. One thing that was interesting, you mentioned Allegro. Allegro was a really cool model from Boris Kozinski's group where basically they said, I want to make this thing scalable by not having any message passing whatsoever. I'm just going to chop everything at the first layer and then everything parallelizes super cleanly because nothing is actually talking to anything farther away. That's, I would say, very much up in the air too. It's a really good strategy for making these things scale to hundreds of thousands of millions of atoms. You take a performance hit in terms of the accuracy. It's a little bit unclear when it's worth it. I wish that those models were just as accurate without any message passing, but it feels like there's still a lot of room to be played with there. Does that make sense?
Yeah, that does. Thanks.
Yeah. Okay. So our team has been working on this area for a while. We run this thing called the Open Catalyst Project. Some of you might have heard of it. There's an open leaderboard. A lot of the models that are the best on the leaderboard, again, were ones that we originally developed for catalysts. From my perspective, I don't think there's anything special about inorganic materials versus catalysts versus molecules. Models that work really well for one tend to work well for the other. It all comes down to like how you scale with data set size and how expressive are your interactions. That's also a super cool feature. It means that like we don't need a special set of models for molecules and materials and surfaces. Like maybe they will be trained differently or maybe they would train on different data sets. But ultimately, this is nice. It would be really annoying if we had different architectures being good for one versus the other, because then we would have 3 parallel tracks of everyone coming up with their own architectures for everything. I am reasonably convinced at this point that if you have something that is state of the art on inorganic materials, it will work on one of these other areas or vice versa. So the approach that we took also in the open catalyst space was one way to make this really interesting for the machine learning community is to make it a sufficiently hard problem that a machine learning expert or AI expert or computer scientist or whatever you want to call them looks at it and says, that is a cool research challenge. And when I started in the space, I had like data sets of 40 or 50,000 points, and I was like quite proud of the 40 or 50,000, but like that's not really the thing that you need to get to hundreds of millions of parameters and really tons of GPUs and scalable and everything else that's going to be interesting. So in the open catalyst space, we released a couple of different data sets, OC20 and OC22, that were huge. And then that basically led to a step change in the community for what was possible in the catalysis space. So we basically took the same approach with inorganic materials, and many of you probably saw this. Basically, again, you look at this leaderboard, you say, it seems like things are getting better, but everyone's training on the same data set. Why is 1.58 million the magic number? It's not, right? It just happens to be the number that was in the materials project at a certain point in time. So why don't we just add more data? So in the fall, we released OMAT 24. So I said we had 2 data sets on catalysis, 1 on direct air capture. There's now 1 for inorganic materials. All of these are sort of moderate level electronic structure calculations. If you add up all 4, it's more than 300 million examples now. We're well over 1 billion hours of compute, like CPU hours, not core hours. That is like a serious number. We don't just release all the data sets online. This is also important for the machine learning community. It's not enough to just dump data. You need to have specific train val test splits and hold out some of the tests. For example, the catalyst and the inorganic materials ones, we never release the test data. If you have predictions, reach out to us and we're happy to evaluate them. There's a live leaderboard for the catalyst one, so you can submit them. But that's really important because it's so easy to like accidentally shuffle and mix data and then get bad results. Like we need to be careful. And maybe the most important thing is that all of this has been open sourced. So Creative Commons, CC4 BY license, you can do whatever you want with it, commercial, non-commercial, it all goes. There's a little bit of an exception for OMAT 24. The license is a little bit different there. There's a terms of use that's basically like, I'm not going to make dangerous things and weapons and other stuff. there's still a lot of freedom in what you're allowed to do with those models, right? Academic things are definitely on the table. So we released OMAT 24. It's more than 100 million of these structures. We basically took things from Materials Project and Alexandria and all the big data sets. One thing that we wanted to do was to really get far from the equilibrium. So we use potentials like our potentials trained on the initial data sets or Magnet or others to basically really jitter all the atoms and generate super high force and energy configurations. And then those are the ones that make up most of the data set. So this is really good if you wanted to get to sort of high temperature simulations that you were talking about. If you want to do 1000 Kelvin where everything is melting and moving and vibrating, you can't just have ground state structures. This was really important. So we have the sort of Boltzmann sampling. We did some short ab initio MD. We did a bunch of rattles. Again, there's not one strategy. We basically tried a bunch of stuff, and that's the 100 million examples that you see in OMAP. And not surprisingly, if you go back and you train models and you have a bunch of diverse data that's far from equilibrium, that has many different elements and many different compositions and many different local environments, your models get better. So the top performing model on the leaderboard right now is an eSEN model, 30 million parameters trained on OMAT and Alexandria and Materials Project. We broke the 20 mil EV per atom barrier. So that's like getting pretty darn close to what I would say is like the limit of the accuracy of these DFT anyways. Like PVE is not the most accurate functional to begin with, but I think we're getting close to saturating. These models are also awesome for phonon spectra. I'll show an example of that in a second. If you go and you look at what happened in the community, so basically there was a steady progression, and there were a couple of these models that were released that were quite interesting, but were not necessarily open. You couldn't actually download the models, or you didn't know what they were trained on. When we released OMAT, we had an Equiformer V2 model, which matched the best proprietary models and actually improved a little bit because the data set was actually larger. And then everything since then, this has all happened just in the past 8 months or so. All of the top models here were trained on OMAT. And so that's really what's allowed all of these models to get as good as they have. If you look at this, most of these are now some variation of OMAT plus some other data set. And so this has been super fun for us. Like if we release a data set, we want other people in the community to use it. We would be very sad if we released a data set and did all that work and then nobody used it afterwards. So this is exactly what we were hoping for. And now we all get to benefit from these awesome models. Phonon spectra, similarly, the old Equiformer models work really well for energies. They don't work great for curvature. Not surprisingly, if you make things smooth and you fix the problems, these new models work really well. That's why the phonon spectra things look so good. So this isn't magic, right? It's just engineering and being careful and going through stuff. But it's a really fun time to be using these models. Last thing, our group doesn't, before I switch gears a little more, our group doesn't just release models of ab initio data sets. We've also done some experimental ones. I don't want to go into a ton of detail, but basically OCX24 was a data set that was computational and experimental that we released last fall. It was basically working with collaborators at the University of Toronto to test a couple of hundred different compositions in catalysis. And those are pretty complicated experiments. You have to like make an arbitrary nanoparticle, get it onto a membrane, get it into a reactor, do the test. It's a very messy environment. Those are not easy experiments to do. And so this data set is the first that we've had that's both computational and experimental, where hopefully it helps people link up the two. I would say it was the first one. We'll hopefully have others. It was not a perfect data set, but nonetheless, I think we need more of these things in the community also to help us test the statistical performance of these models. Like as we get better and better on the computational side, eventually we need to say, how good are these at actually predicting what happens in real life? And so we need the same sort of data sets for the experimental side too. Yeah.
I have a question there. So
Yeah.
when you, because you draw pictures including a battery, so is your data set, does that include performance in a device, or is
It is at a relatively high current density. So this looks like a battery. It's not actually a battery. What it is it's an electrochemical cell. You basically apply a potential across this stack. And what you're doing is you're taking CO2 that's coming in and you're adding hydrogen, you're reducing it until eventually something comes out. And that something might be carbon monoxide. It might be ethylene or ethanol. It might be methane. There's many, many, many different things you can make. The goal in that space is to usually try and make one particular high value product like ethylene. But a side reaction you could do is you could take water and you could rip it apart, and you could just end up with making a bunch of hydrogen gas instead. So that's also a valid reaction. There are electrolyzers that people do that for if you want to make hydrogen.
Are you predicting all of these? So are you actually
Yes.
predicting without ever building this box just
Yes.
from your initial calculation?
Yes, that is the goal of what we were trying to do. And if you look at the case of for predicting whether or not one of these things makes hydrogen just with water around, I would say there is statistically meaningful predictive power between what you can correlate with ab initio predicted properties and what happens experimentally. But that chemistry is also pretty easy. If you look at the CO2 case, I would say like there's a correlation that's more than 0, but it's not as high as I would have hoped. And so the hope is that someone comes along with an even better model to connect the two. But these are different class of models. These are, you have 100 million calculations that you might want to correlate, and you have 200 data points experimentally, and somehow you have to build the best model with those. It's a different game to play. Yeah. Make sense? Okay. If you love Catalysis, feel free to chat with me afterwards or send an email, and I'm happy to go into more details there. Okay, so with the last 10, 20 minutes, whatever, I also wanted to talk a little bit about some of the work on generative models we've done, because this is super topical. There's a lot of fun new ideas that are coming in that community right now. One of the nice things about working at FAIR is that we have access to a bunch of researchers who are working on state-of-the-art things in language and vision. So for example, this Meta Movie Gen has a video component, and it also has an audio component. And the audio component of this release last year was basically a flow matching method that was developed within FAIR. Like there's been a lot of interest in flow matching methods. I would say like 2 of the founders of that field, 2 of the world experts happen to be at FAIR right now doing these things for the audio case. And because we're all within FAIR, we can collaborate with them easily. And so we've been able to work on things like flow matching for materials, basically hire manifolds to basically do diffusion on. I'll talk a little bit more about this in a second. We've had a few now where we either take language models or flow matching methods or combinations or diffusion transformers. All of these are different ways of solving this problem of how do I generate the next material. And we probably all saw the really cool MatterGen release. That was super fun for the community. I think that's really exciting. I think there's going to be a steady progression in the models, just like there was in the machine learning potentials. This is a super active area right now. And it's also really fun. Whenever you go to one of these ML conferences, it's so fun to see like 10, 20, 30 different examples now of different methods that people have come up with in the space. So I'm not going to talk about these 3 because from my perspective, it's last year. They're already out of date. We don't need to talk about them. But I'm happy to talk offline if you want. I wanted to touch on this last one, this all-atom diffusion transformers, because it's hot off the press and it was one of the summer interns. Chaitanya is a PhD student at the University of Cambridge. He was a summer intern and worked with me in Anirudh last summer. Super, super talented, sort of in the AI, GNN, biology space. He's actually going to be coming and doing a postdoc at Stanford in the fall. So he'll also be in this sort of community of people. You should reach out to him. He's super fun to talk to. And basically, one of the things that we noticed was that in this space, there were a bunch of people who were building models to generate inorganic materials. And there were also a bunch of people who were building models to generate low energy conformers of small molecules or new hypothetical drug-like molecules, or how a small molecule might fit into a protein assembly, or how I might predict the folded structure of a protein. What we didn't see was how could you build one model that could connect the 2. There were basically 2 parallel groups of people who were solving basically the same problem, and they treated it as 2 completely different areas. Nobody was using the same data. So what we did was we basically built a little prototype system, and we're trying to find a way to do this. I don't think we solved the complete problem, but we were able to get everything in one form, and some of the results do look quite interesting. So the fundamental idea, the first one is basically it's all atoms. Like at the end of the day, if you're doing carbons with hydrogens and inorganic materials or small molecules, like it's all atoms. It's not actually that different. They are sort of 2 different communities, but it's not wildly different distributions that you're drawing from. So we had to find a way to embed both molecules and materials in the same space. And anyone who has done this knows that one of the first questions is basically all the materials people like periodic boundary conditions where you repeat the thing over and over. And all the small molecule people use codes where you can't do that. And so they never have it. And so that's like fundamental challenge number one. So basically what we did was we sort of cheated. We said there's going to be a vector that's what is the type of atom. So length n is the number of atoms in this unit cell. We're going to have the number of the 3D coordinates of each atom in absolute positions. We're also going to have the fractional coordinates, which should be the absolute coordinates divided by the unit cell if there is a unit cell. And we're going to have the lattice parameters for the unit cell if there's a unit cell. If it's a molecule, this thing won't exist. And if it's a molecule, this thing also won't exist, or I can sort of augment it by having a fictitious unit cell. This was not like the solution I was hoping would win. I was hoping that we could just do one or the other, but ultimately the thing that worked the best was basically to have two different tracks.
But you don't have the symmetry.
No symmetry group. That's right. Yeah. You can argue that both ways.
I'm just observing.
No, these are all interesting questions, right? It's the more bias you put in, the weirder your manifold looks like. Sometimes it makes things harder to learn. Sometimes it then becomes the right manifold and that's the right thing. Yeah, I've been surprised. Okay, so basically, if you're doing a molecule, you basically just set these to null and don't consider them in the loss function. So far, so good. If you're doing periodic, you have all the things. Okay, so that was choice number one, and we tried a bunch of different things, but this is the one that ended up in the manuscript. And so the second thing we did was we wanted an encoder. So basically, we wanted to take these atom types and these coordinates in unit cells and their graph structure. And then we wanted to find an embedding that we could then use. And we tried a bunch of different geometric GNNs from very, very simple things, which didn't have very much equivariance or other things built in, to very complicated ones like equiformer inside of a group, which we consider to be like pretty close to the state of the art. Most of the geometric GNNs try and encode these physical symmetries. So like usually the right thing to do, and I talked a lot about this with eSEN, like you make a bunch of choices that you think are going to be reasonable, and those things often help in that case. Not 100% of the time, but they often do. And that includes things like rotational and translational equivariance, both for the final outputs and maybe also for some of the internal representations. But you can also get transformers to learn a lot of the same things by basically augmenting the data. So if every time I show it the data, I just randomly rotate it or randomly flip things around or flip it around or do different handedness or symmetries, I can often get the transformer to basically come up with a rule that's still going to work. And because the goal in this space is generate a new material, it's maybe a little less important than predicting the property. Like the people who do property prediction often like really, really, really care. Like, did you do the property prediction well? The people who just want a hypothetical new material, they can take that thing and then study it. But like, as long as you give them a realistic material, they might be like, maybe they don't care quite as much about what the method came from. But again, these are decisions. So we ended up using a standard transformer. I'm happy to talk about this at the end or go through the paper. If you look at the paper, basically we tried lots of stuff. And at the end of the day, the simplest thing where we did nothing complicated was the one that won. That was not how I thought it was going to go. We spent a lot of time going down that rabbit hole, but nevertheless, that's the best one in the paper. The second idea that we had was there's been a bunch of work in latent diffusion models. And basically this led to this method that we call ADDIT, the all-atom diffusion transformer. And basically what we're doing is we learn an autoencoder that takes molecules and materials and learns a latent representation. And then we do the diffusion in that latent space. And then once we find a sample that we think is going to be interesting after reversing the diffusion, then we basically decode it to find the material or the molecule that we think is going to be exciting or interesting. And that's a little bit different than some of the other spaces, some of the other models in the space where you just do diffusion directly on the coordinates or on fractional coordinates or something else, rather than in this intermediate latent space. So this first stage is you train an autoencoder. This looks just like a normal autoencoder. We throw all these together. This was MP20 and a small molecule data set. We train it all at the same time with augmentation and try and learn a reasonable latent representation. Again, we do data augmentation to get equivariance, but you can make other choices there. And then the second is we basically...
Did you put that in or did you just rotate a few and it automatically came?
We rotated them and then it is approximately equivariant, but not perfectly. It learned a rule that was good enough for what we wanted. I don't even want to come close to making a claim that the final thing is actually equivariant. My guess is it's not. what it is good enough to come up with a view of the distribution and learn a sample from it.
So the final model is based on no occupation standard.
100%. And again, when we started this, the sort of fundamental assumption was that the latest fanciest GNNs like Equiformer or eSEN or pick your other favorite model is the right encoder because it was the right thing to get the right representation to predict energies. But actually you pay a price in terms of like how many parameters you have and how easy it is to use. And the hand-wavy explanation is the price you pay for that is worse than the speed that you get for just training longer and coming up with a better outcome. But again, if any one of you wants to give this a shot and you find that a super cool encoder actually does better, please send me an email. I'm open to data. Okay, so then the second stage is after we have this encoder, I basically want to learn the distribution in the latent space that corresponds to molecules and materials. And that I do with a diffusion transformer in the latent space. So there's two different transformers happening here. And the cool thing then is basically I can condition this thing. So I can basically take things like the time step of where I want to go, like far in the relaxation or early, relaxation basically being closer to the distribution or not, or I can condition on some property, and I can throw in a bunch of noise and this conditioning, and it will eventually spit out a latent vector that I can then use in a decoder to predict the final molecule material. Again, these are like very standard things in the image community, but people hadn't done it in the material space as far as we could tell.
So does that mean I essentially could imagine having a slider which says my first autoencoder encodes a lot or almost not at all, and then in the middle you just run your standard diffusion transformer? Or
yeah, exactly. You basically want to do your diffusion in a space where it's as easy as possible to move around, because if you have to worry about atoms overlapping and the representation says, oh no, these two atoms shouldn't overlap, like it can actually be a little bit difficult to say how to denoise a chemical structure. But what you want is to just like move to a distribution in a place where there's no barriers and it's smooth and you can do it fast and you can like go straight to the answer. And then you take that answer and you decode it to the final solution. And so just a couple of experiments here. So what we want to do is we want to basically screen generate everywhere. So molecules, proteins, small molecules, catalysts, everything, MOFs. What we did in the paper, we basically had small molecules and inorganic crystals. And we basically looked at whether co-training helped in the generation. So if you train just on materials or just on molecules or both, is that better or worse than one alone? So basically the way that we do this is we look at things like, if I take an inorganic material, is it valid? Like the volume is reasonable and no atoms are overlapping. And is the composition reasonable? Like I'm not violating any rules of anions and cations or charge or whatever. And is it stable? If I use my favorite machine learning potential, is it actually low energy compared to the whole? These are sort of standard things in the community now. And what was super interesting was we took two models that our group had developed, one equivariant diffusion model and another language model. And both of these are pretty good models. So this language model, FlowLM, close to 100% structural validity, 90% composition, 90% structure and composition, and about 67% metastability. That's pretty good. Like 2/3 of the time it spits out a structure that you can take the materials project and say, please run this thing, and it might actually show up. That's pretty darn cool. The next two experiments we did were, let's take this adit, an equivariant one or a regular one. And basically this was the experiment that convinced us that we don't need these fancy equivariant encoders. The results were actually a little bit better when we did the super simple transformer and we threw everything out. And again, this was not very satisfying as someone with the physics background, but nonetheless, that's what we found. So this was cool. This was like the first fun experiment from the paper, from the internship. This got to about 80%, which is a pretty big jump. And that just said that like as a generative model, it felt like this thing might have a little bit of promise at being competitive with what was already like, I think, pretty close to state of the art compared to models out in the open. And then the really fun experiment was basically if we trained on both at the same time, we could basically reproduce the results and also start generating molecules. And none of these things are wildly different than the ones alone, but nonetheless, this is a model that can basically, you can ask it to spit out molecules and materials and it will do both at the same time. So that was pretty cool. There were some follow-up experiments in this paper where basically we go through and we try other variations of this. maybe closer to your home and for the people doing MOFs, the last thing I asked Chaitanya to do, I said, okay, like if you train on molecules and materials, the obvious thing I'm going to ask you to do that's halfway in between is generate MOFs, which is like sort of this murky space halfway in between. And so the very last figure in NDSI, I was able to convince him to run some of those experiments. It does work. I would say it didn't like hit it out of the box, but nonetheless, you can also encode MOFs at the same time, which is pretty darn cool.
What is your number there?
I forget the numbers.
50%,
I don't
20%?
want to say because it's going to be wrong, but the numbers are in the paper. This is also all open source. So you can go play with it. The checkpoint is not available online. Chaitanya, I think, might have reproduced it on his own in Cambridge afterwards. So if you're interested, you can maybe send him an email. But these are things that you can play around with, and the paper went into a bunch more detail. Okay, so I think I'm right about an hour, but we have tons of time for discussion. Just a couple of takeaways. So first, this is really a super exciting time to be in AI. Like, I don't know if you all feel the same energy I do, but like when I was finishing my PhD, there were no AI for material startups except for like just one or two examples. And now they're just like coming left and right constantly. And all of the big industrial labs are in this space, and all the chemical materials companies are excited and doing new AI efforts and everything. For all the people in this room, this is a really fun time to be doing this sort of work. These models, like I think like the community is almost like a little bit underselling how good some of these models are, especially in the inorganic space. Like PBE is not the perfect level of theory, and I'm not going to claim it is. But basically, we have models that just out of the box work at PBE level for basically everything you throw at it, including a bunch of new things like high entropy alloys and other materials. And you're not going to be able to solve every scientific problem with those, but these are things that are now basically free. And they're things that when I did this 10 years ago, I would have spent 2 days running a stupid calculation. And now we can run in like 3 seconds and it gets the right answer. And we shouldn't take that for granted. Like, this is basically magic from my perspective. For anyone who can get away with sort of PBE level theory, this is really, really, really fun. These open data sets and models are really important. So that's why our group releases this stuff openly. It's really fun for other people to develop new models. A bunch of the best models were not developed in-house, or they were combinations of us and someone else. Like Equiformer V2 was Tess Schmidt's group, who Tess was also a postdoc here at Berkeley originally. She's now at MIT. Students going back and forth and doing internships. Everyone benefits from this moving as fast as possible. And the third thing, I think we're also very lucky to be in the Bay Area. Like, there's just so many companies and research groups and national labs and efforts going on right now. I don't think we like all talk as much as we should. Like, most of my friends that I see in the community, I see at MRS or a random conference, even though they live like 20 miles down the peninsula. But nonetheless, I just want to remind everyone that like we're extremely fortunate to be in a space where there's so many fun people doing this work. If you're ever interested, feel free to send me an email or reach out, or you want to have lunch or whatever. We're all very close at the end of the day. Very last thing, I didn't talk at all about the code, but all of this is open science. So there's a GitHub repo, there's tutorials, there's demos, there's other stuff. You can do whatever you want with it for the most part. If anything is not working there, post a GitHub issue. We won't be unhappy. We will usually try and fix it as soon as we can. Even better, solve it and submit a PR. And we are really happy to approve PRs. That's like by far the best thing. We get those more and more frequently now. Last thing,